We just drew how a neural network thinks. Now let's build the very same network in real code, one line at a time. Let's write this network from a blank file, one line at a time. First, the tools. Torch is the main library. We also bring in nn, which holds the building blocks for networks, and f, a box of handy math functions. 3 short lines, and we are ready to build. Now the network itself. We wrap it in something called sequential. Sequential just means take these pieces and run them in order, from top to bottom. The output of one becomes the input of the next. Inside, we stack the pieces we just learned. A linear layer, which is a full layer of neurons, then a ReLU bend to curve the data, then another linear, and another bend. And finally, a last layer that shrinks everything down to 10 scores, one for each class we want to recognize. Watch the network on the right grow as each line appears. Here is something the drawing could not really show you. Every linear layer quietly holds a big grid of weights, the numbers it has learned. We can ask the first layer for the shape of its weight grid. It comes back as 256 by 784. That is, 256 neurons, each one looking at all 784 inputs. Multiply those, and this single layer holds over 200,000 numbers. And the network learns every single one of them, on its own, during training. Time to run it. We make some fake input, a batch of 32 images, each one 784 numbers long. Working on a whole batch at once is just faster than doing them one by one. To run the network, we simply call net of x. That is it. Out the other side come the raw scores. If we print the shape, we get 32 by 10. That is 10 scores for each of our 32 images. This one short call is the entire forward pass we animated earlier. Those raw scores are hard to read, so Softmax turns each row into clean percentages that add up to 100. Now we can actually say how sure the network is. And argmax simply picks the tallest bar in each row, which gives us the one final predicted class. Here the network is most sure about cat. Next we measure how wrong the network is, using a loss. And here is the trap that catches almost every beginner. Cross-entropy loss in PyTorch wants the raw logits, the scores from before Softmax, not the nice percentages we just made. Why? Because it quietly runs Softmax inside itself in a safer, more stable way. So if you run Softmax first and hand it the percentages, you squash the signal twice, and your network learns slowly or not at all. So remember this. Give the loss the raw logits and let it do the rest. So far, the network has only made a guess. How does it actually get better? That is the training step, and it is just 3 small moves. First, we pick an optimizer atom and hand it all the weights. The optimizer is the helper that will update them. Then, backward looks at the loss and fills in the gradients. A gradient is just the share of the blame for each weight, and which way to move it. Step then nudges every weight a tiny bit in the better direction. And zero grad wipes the gradients clean, so they do not pile up into the next batch. Run this little loop over and over, on batch after batch, and the loss slowly falls. The guesses get better. That falling curve is what learning actually looks like. One last practical tip. By default, everything runs on the CPU. But neural networks love a graphics card, a GPU, which does this kind of math much faster. This one line picks a GPU if you have one, and otherwise falls back to the CPU. Then we just move the network and the data over with .2 device. Same code, same result, only faster. And that is the whole story in code, mirroring every picture we drew. Build, run, measure, and improve. The single line, loss.backward, is where the real magic hides. We open it up next in backpropagation.